we'll focus on the two-sample t-test. Earlier, we talked about a one-sample t-test where we took a particular sample of data and were interested in whether the process was on target at a given value. And we did a one-sample t-test. We're now extending that to the two-sample t-test. So earlier, we took one sample of data and we looked at whether we were on target. So we took one sample of data, found the mean from that particular sample, and used it to give us some idea through a hypothesis test of whether the true mean of that distribution was on target. Now we're interested in extending that to two samples. So now we're interested in whether two distinct populations have the same average. Population examples could be two different operators, two different machines, two different days of production, two levels for a particular factor, like a low level versus a high level, two brands, two suppliers of some raw material. We start by taking a random sample from each of these populations. So we take a random sample from each population. In general, it is not required that the sample size we take from each population is the same. However, it does turn out to be a more powerful test if we use the same sample size, and most software will actually require that the same sample size be taken before it will calculate the appropriate sample size needed to conduct the test. However, if it costs way more to sample from one of the populations than the other, it's certainly reasonable in general to use a smaller sample size from the expensive one and a little bigger sample size from the least expensive one. Consider an example involving two suppliers of some raw material. The raw material is then turned into some product, and what we're interested in doing is measuring the breaking strength of that product. We will take sample sizes of 10 from each of the two suppliers. So in this case, we are using equal sample sizes. Recall that in general, the null hypothesis refers to nothing is going on or everything is okay. In our particular example, that refers to the two population means being identical. There's no difference between the true mean breaking strength of the two suppliers. It is common when performing a two-sample t-test to assume that we have equal population variances. So each population has the same variation. We're assuming that, and then what we're interested in testing is whether the means are different. If we look at a figure or a graph, that would then give us this kind of picture with that assumption. Because we are assuming that we have the same variation estimate, then our curves, here drawn with normal curves because that is another assumption, would be bell-shaped curves with the same variation or same type of spread. So what we're looking at then is just whether one curve is shifted from the other. In this particular picture, I've drawn supplier 1 with a mean of 150 and supplier 2 with a mean of 160. So we're just looking to see, is that shift of 10 units on average in the breaking strength, is that enough to reject the null hypothesis and say there is some difference between these two, and supplier 2 seems to have a little bit higher breaking strength on average. So let's begin The 5-step procedure we have been following in other PowerPoint presentations for basic statistics, and that begins with state the hypotheses. Well, we said the null hypothesis in general is nothing is going on, or everything is okay, which in our case would refer to the two means being equal, mu1 equal mu2. Our alternative will be a simple not equal to case where we're not trying ahead of time to prove 1 is bigger than 2 or 2 is bigger than 1. We just want to know, is there any difference between the two? We typically rewrite that, rearrange the equation, moving one of the means to the other side of the equality, so that we end up with something like mu1 minus mu2 equals 0 versus not equal to. We, of course, can subtract mu2 minus mu1. Subtraction order is not important in the problem. This allows us to now have a target value. Recall that the same analysis or same general conclusion of the analysis of do we reject the null hypothesis or fail to reject the null hypothesis can simply be done by looking at a confidence interval and checking to see whether your target value is inside the confidence interval. If it is, we fail to reject, and if it is not, we reject. This now gives us a value to check for our confidence interval. So the confidence interval will be on the quantity mu1 minus mu2, not individual confidence intervals. This is a two-sided case. We could look at the one-sided cases if we were interested in. Step 2 is to state the test statistic, our sort of summary value from the data. Our estimator is going to involve the sample mean. So we need an estimator for the true mean difference. So the true mean difference is mu1 minus mu2. We need an estimator for that. The natural estimator, I believe, would be the difference in the sample means subtracted in the same order as the quantity we're interested in. So thus, y bar 1 minus y bar 2 would be our estimator for mu1 minus mu2. Now, y bar 1 minus y bar 2 has a variance of sigma 1 squared over n1 plus sigma squared 2 over n2. Now again, that is generic in case the n's are not the same size. But notice that if we just had a single mean, y bar, it would have variation sigma squared over n. So all we've done is extended that where we're adding them together because they are independent of each other. Well, we are assuming that sigma 1 squared is equal to sigma 2 squared. That was our assumption, equal population variances. So let's replace sigma 1 squared and sigma 2 squared by just sigma squared as an example. We could call it anything we want, but let's just call it sigma squared. That means that the variance formula above, when we substitute just sigma squared in for both of those terms, becomes simply sigma squared times 1 over n1 plus 1 over n2. Notice that that would even reduce further if the n's were equal to simply sigma squared times 2 over n. So we need an estimate of, or an estimator for sigma squared. It seems natural that we should use just one estimate since there's only one sigma squared. And because we have two estimates of the sample variation, S1 squared and S2 squared, we will pool those together to form a single estimate of sigma squared, and we'll call that estimator S squared sub P, or S squared pooled. You notice that it is just sort of a weighted average or a pooling of the two individual sample variances. It is important to also note that if n1 and n2 are equal to just say n, for example, then when you substitute that in, the formula will reduce to just s1 squared plus s2 squared over 2, or simply the average of the two sample variances. Now we actually need the standard deviation, not the variance for the estimator, because our t-statistic is always divided by a standard deviation, not a variance. So we simply square root the formula from before. We put SP squared in as our estimator for sigma squared, and then square root that whole quantity. Gives us S sub P, and then square root of 1 over N1 plus 1 over N2. So we could then form a t-statistic, which is going to be our estimator, y bar 1 minus y bar 2, minus 0. The 0 is just representing the target value, because mu1 minus mu2 equals 0. It's not necessary to put in the equation. I put it in for completeness. Divided by the standard deviation, SP, square root of 1 over N1 plus 1 over N2. Next to that, I've written that this is really distance over variation. Recall that in the one sample t-test, I focused on that it's really the t-statistic is looking at distance over variation, where distance in the one sample t was how far from target you were. The further you were, the more likely something is going on, but to know exactly how far it is in terms of a distribution, we need to have an estimate of variation. Doing the same thing here. Now what we're talking about is distances, how far are the two means from each other. The further apart they are, the more likely that something is going on. So that's our distance now. But again, we cannot say that that distance is big or small unless we have an idea of variation. Step 3 is to state the critical region. We are going to use the alternative hypothesis of not equal to, so we reject the null hypothesis if the absolute value of our test statistic, t, is bigger than t of alpha over 2 with some degrees of freedom. Now, the appropriate degrees of freedom for a two-sample t-test with equal variation, assuming equal variation, is n1 plus n2 minus 2. Actually, that's pretty straightforward, really, if you think about it, because if we did a single t, it was just n minus 1, one sample. So now I've got two samples. So if we take n1 plus n2 minus 2 and split it up to rewrite it as n1 minus 1 plus n2 minus 1, notice that what you're doing is you're getting the same type of degrees of freedom we got in a one-sample t-test from each of the two samples, and we're putting them together. So for our particular example, that results in 18 degrees of freedom, 10 plus 10 minus 2, and of alpha over 2 of 0.025, assuming we use alpha of 0.05, yields 2.1. So from a picture point of view, what we're looking at is if t is bigger on the right-hand side than t alpha over 2 or left-hand side, and we write the critical region as absolute value to just force us to be on the right-hand side of that curve. Alternatively, most software packages will calculate the p-value instead, and the p-value will simply be the probability that we're bigger than the absolute value of our test statistic. That forces us on the right side of the curve. We find that probability, and then we multiply it by 2 because we could have, we're splitting the alpha in 2, and so that we can compare it directly to alpha, we're multiplying by 2. The next step is to conduct the experiment, collect the data, and to calculate the test statistic. The data is sitting there in that table. We get the summary values, y bar 1, 149.18, y bar 2, 154.33. We get the two sample variances, S1 squared and S2 squared, and then I've calculated SP. Do notice that SP there is not the SP squared, it's SP. SP squared will simply be the average of the two S squareds, S1 squared plus S2 squared over 2, because we took the same sample size, 10. The test statistic then is the difference in the two sample means divided by SP square root of 1 over 10 plus 1 over 10. That becomes negative 2.53. Could also construct a confidence interval. Another very common way to go is to construct a confidence interval. Confidence intervals in general are of the form estimator plus or minus table value for confidence times the standard deviation. So our estimator is y bar 1 minus y bar 2. The t n1 plus n2 minus 2 degrees of freedom alpha over 2, which would be the same 2.1 from the critical region, is our table value. And our standard deviation, again, is SP times the quantity square root 1 over m1 plus 1 over m2. Putting all the numbers in and cranking that out, we get an interval of minus 9.426 to minus 0.874. We can interpret this interval as we are 95% confident that the difference between the two means is as little as 0.874 or as big as 9.426. Or we could say we're 95% confident that the true mean for supplier 2 is larger than supplier 1's mean, true mean, by as little as 0.874 or as much as 9.426. If this interval contains 0, which it does not, but if it did, then it would suggest there's no statistical difference between the two suppliers, because that's our target value for mu1 minus mu2. Let's investigate that confidence idea a little bit further. Suppose we are subtracting 1 minus 2, supplier 1 minus supplier 2, as we did in our example. Let's suppose we want to maximize the breaking strength. And we're going to look at 95% confidence intervals. It is important you have a goal in mind of either maximizing or minimizing, and also which way you subtract it before you can actually make a good interpretation of the confidence interval. So let's suppose that the 95% confidence interval on mu1 minus mu2 is 2 to 8. So the first question is 0 in the interval? The answer is no. So therefore, one of the suppliers must be better, and in particular, supplier 1 is better, because if the whole interval is positive, then mu1 must be always bigger than mu2, so that that subtraction always has positive numbers. We can reverse that. What if the interval is minus 5 to minus 1? 0 is not in that interval. The whole interval is negative. This, like our example, suggests supplier 2 is actually bigger because mu1 minus mu2 is always negative, so therefore 2 must be bigger. Now what if I have minus 1 to 4, the last line in the table? First, notice that 0 is in the interval, and which suggests there's no statistical difference or no statistical significantly different between those two means. Why is that? Well, on the minus 1 to 0 part of the scale, we would say that supplier 2 is better. But on the 0 to 4 part, the positive part, you would be in line 1 and you'd say supplier 1 is better. So what you're saying is sometimes supplier 1 is better, sometimes supplier 2 is better. That sort of means that there's not really any difference between the two. Because of the simplicity of just checking the interval for 0, many practitioners prefer just looking at a confidence interval and seeing if 0 is in the interval. If it is, well, then we say there's no statistical difference. And if it's not, based on whether it's positive or negative, they decide which mean is bigger. And then we can quantify how much bigger it is by using that interval. So many times if you reject the null hypothesis, you're going to use a confidence interval to quantify the magnitude of the difference between the two. So why not just go to the confidence interval directly and check the interval? A similar approach using confidence intervals can be done with something called multiple comparisons in analysis of variance. So if you're comparing, say, 4 suppliers, you begin with an F-test, which says that at least one of the suppliers is different. But then to understand which suppliers are possibly different from which other suppliers, we use what's called multiple comparisons. And one approach is to find confidence intervals and look for zero. Now those confidence intervals are a little more sophisticated than ours because they control the overall type 1 error rate across all the comparisons. But in general, the same kind of approach of looking for zero. So finally, let's reach a conclusion. Since t of 2.53 in absolute value is bigger than 2.1, our critical value, or if we actually found the p-value from our example, we would find that that's 0.021. Since that is less than the 0.05, or since the zero target value is not in our confidence interval, since it was all negative, all of this leads us to reject the null hypothesis. So therefore, there is sufficient evidence to show that the true mean breaking strength is higher for supplier 2. Now, one of our assumptions right up front was that we had equal variances. We're also assuming normality. If it is known that the population variances are not equal, then we can use a different variance or standard deviation estimate. A standard deviation estimate would then be the square root of S1 squared over N1 plus S2 squared over N2. In other words, since we're not assuming a single sigma squared, we don't factor that out and form a pooled. We treat the estimates separately. Now, that does impact things because the resulting test statistic, the t-value that what we call a t, is actually not an exact t-test. It's actually an approximate t-test. And it has slightly different degrees of freedom. It's not simply n1 plus n2 minus 2 anymore. At this point, you really need to use software. I'm not going to go through that. You should be able to find it in any sort of textbook if you're interested in looking it up, but really need software at that point. Finally, our last thing is we did assume that the data was either normally distributed, the distributions were normally distributed, or that we took a large enough sample size so that the central limit theorem would kick in, and that would guarantee that the sample means would follow a normal distribution. Here we have two probability plots, the dots representing the data, and what we're looking at is if they follow close to the blue line, where the blue line represents a normal distribution, then we could feel comfortable with our assumption of normality. The graphs look perfectly fine. There's no large deviations from that blue line, so normality was a reasonable assumption for what we did in our two-sample t-test. If neither is true, variances are not equal and we do not want to use the approximate test, or our data is not normally distributed, then the most common solution to that problem would be to use a transformation. So to transform both columns of data into a different scale that the assumptions are met on, and then do our analysis there. Common transformations are the log and square root. And if that does not work, there is also procedures designed out there to handle non-normal data. Those are typically called non-parametric tests, where we assume no shape to the distribution at all, and we can solve that. In particular, for a two-sample t-test, we use what is referred to as the Mann-Whitney test as the non-parametric alternative to the two-sample t-test.